Got it? All right, it's just us. It's a good day. Heavenly Father, we thank you for this day. Thank you for the CFA people enjoying all the other classes. And help us to have a good day today. Help us to glorify you what we do and to learn something. Amen. Okay, so here we go. We are now both feet completely firmly planted in section 3.4. I think this is lecture 28, but I kind of lose count. It feels like lecture 28. And we're going to talk about ring homomorphisms for the most part. All right, so what is a ring homomorphism? Let us remind ourselves the terms and conditions. If R and S are rings, right, then we have theta going from R to S is a ring homomorphism. What three things are required of a ring homomorphism? Yeah, one, theta of x plus y is theta of x plus theta of y. Number two, theta of xy is theta of x, theta of y. And because our rings have identity, we also have to insist that 1 goes to 1. So 1 in R maps to the 1 in S. These are required for our ring homomorphism. So there are lots of examples of this. Let me just rattle off a couple for you. One, and this is probably important, we can look at pi, the coset map from R to R mod A for A and ideal, right? And that would be pi of x equals to x plus A, right? So the fact that that's a ring homomorphism is basically the definition of the factor ring, right? So that's a ring homomorphism. Number two, and this is actually an example, a case of number one. If we look at, I'll give it a name, psi, mapping from the integers to the integers modulo n by psi of x equal to x bar, well, that is also a ring homomorphism, right? There are other ones. If we have, we can define pi 1 that goes from the Cartesian product of a ring and a ring to the ring again, or pi 2, which goes from the Cartesian product of R and R to R again, where, I may have said these before, I'm sorry if I have, if I'm in reruns right now, my apologies. So pi 1 of xy would just be just x, you know, and pi 2 we could just use y. And it's easy enough to prove that those are in fact ring homomorphisms. Of course, you could have more, right? You could have like a Cartesian product of n things and still look at projections onto any of the factors, or some subset of the factors in kind of a natural way, right? I could have like pi of x, y, z, and if I just kept x and y, that would give me a homomorphism from R cross R to R cross R, right? You could play games with more of these. 4, this is a notation that I don't think I've talked about yet, but I've been meaning to for lectures and lectures at this point. Because this notation, I haven't seen really anywhere but Nicholson, and I like this notation, actually. I think it's really cool. So by this, he means what? This is the ring of 2 by 2 matrices where the 1 component is 0, and the other 3 components are arbitrary things from a ring, right? This is a sneaky way of giving you a subset of M2R, right? It's a very slick notation. I like it. You know, it means what it means. I don't want to read too much into the notation. I mean, I can say this much. See, but now that I'm writing this, you're making me undo the goodness. But the point is that I didn't have to write this because we all knew what it meant. But I respect your right to say that that's the zero ring. It's fine. But that is the meaning of that notation, obviously. Okay, so here you can define a ring homomorphism as follows. You just keep R and T. Okay. What's that? Yeah, it does. And so to see that, you'd actually have to multiply it out. Here, I'll take a minute to do it. R1, S1, T1 times R2, S2, T2. What happens when we multiply these matrices? Let's just look at that. So we get R1, R2, and we get 0. Down here, we get T1, T2. And up here, we get fun stuff. Let's see here, what do we get? We get R1, S2 plus S1, T2. So if you look at, let me call this thing matrix 1, matrix 2, right? This is matrix 1 times matrix 2. It's fairly clear from this that the theta of the product of M1 and M2, right, is going to be equal to theta of M1 times theta of M2, because this is what? This is R1, R2, comma T1, T2, right? And that's equal to R1, T1 times R2, T2. What have I done? Oh, R2, T2. The best puns are the unintentional ones. It's true. Theorem. Of course, there's more to show that that's actually a ring homomorphism. You have to check everything there, right? But that's kind of the most interesting one. And so, would this be 1-to-1? No, certainly not, right? It's completely losing track of whatever happens in the 1-2 spot, right? In fact, the kernel of this would look like what? I think it would be, which kind of kernel? It's always additive, you're right. So yeah, you're right, 0R, 0, 0. Thank you. I had to get that out of my system. Okay, so R and S are rings. If we have R and S rings, and we have theta that maps from R to S onto, then if theta preserves addition and multiplication, then theta is ring homomorphism. Now, all I'm really saying, let me be a little bit more precise here. What we're really just saying is that if you have a surjection, and your surjection satisfies items 1 and 2 here, it automatically satisfies item 3 as well. All right? In other words, 1 maps to 1 is automatic if we have onto. And here's the argument for that. If we let theta of 1r, let's call that E, all right? And if S is an element of S, hence S is equal to theta of X by onto, by surjectivity, let's say, then what do we get? We get S times E is equal to theta of X times theta of 1r, right? But it preserves multiplication, so that's theta of X times 1r, which is theta of X, which is S, right? And likewise, ES is equal to S. Hence, E is in fact the 1 for S, and theta of 1R is equal to 1S, and that completes the deal. That means theta is a ring homomorphism. Okay. Yeah.
Hints might be used the fact that it preserves addition.
Well, but if I didn't have that, they wouldn't be a ring homomorphism. But you're right. I think we could state a leaner version of this theorem that would be lemma. If you have a mapping which is onto and preserves multiplication, it must map the identity to the identity.
In fact, I think that's one we're training.
Oops. Well, it's a training. It's harmonic. So theorem 1 of, again, section 3.4. 1, theta of 0 equals to 0. 2, theta of minus r is equal to minus theta of r. 3, theta of kr is equal to k theta of r. 4, theta of r to the power n is equal to theta of r to the power n. I'll add some parentheses there in a second. If u is a unit in the ring, then theta of u to the integer power k is equal to theta of u to the integer power k for all possible integer powers. The one above is for all n greater than or equal to 0 in Z. And up above here, this is for all k in Z. And, oh, I'm sorry. What happened there? Oh, I've got a typo in my notes. Don't mind me. Let me add some parentheses there for emphasis. Now, the proof of these are all pretty straightforward. So I won't really get into it. I mean, in fact, really, 1 and 2 and 3, these all belong to what? I mean, if you look at it, these 3 we've already proved before. Those are properties of the abelian group structure of the ring, right? And so those are identities we know for group homomorphisms written in the notation for an additive group. That's just usual group homomorphism properties. Now, 4 and 5, well, those are new. But you can, yeah.
5, does that imply that every homomorphism maps units to units?
In fact, it does, right? So number 5 is exactly what you need to prove that units map to units, right? And also, well, I guess 4 gives us that nilpotents map to nilpotents, right? Notice if r to the n is equal to 0 for some n, right? Then that implies that theta of r to the n is equal to theta of r to the n, right? But that's equal to theta 0. So this is equal to 0. There we go. It's rectangular logic. Now, there is a caveat there. I mean, technically speaking, if you want it to be a non-zero nilpotent, we do need that the image of R is what? Non-zero, right? You could have the 0 homomorphism. It doesn't map to interesting nilpotents. I guess 0 is a nilpotent element, right? But honestly, when I think of nilpotent, I think of something non-zero that somehow powers to 0. That's the interesting stuff. The fact that 0 is nilpotent is like, yeah, great. Okay. But yes, application, if R is a unit, theta of R is a unit. If R is an idempotent, theta of R is an idempotent. If R is nilpotent, then theta of R is nilpotent. So we map units to units, idempotents to idempotents, and nilpotents to nilpotents, even if the inverse map doesn't exist. This is just to for ring homomorphisms. There's the example 7 and the examples that follow, there's a general idea, and I'm going to try to state it in a little bit more fuzzy way. General concept. New homomorphisms from old. And this is really a specific context. I mean, of course, you can do things like compose them if that's possible, or you could, I mean, there's various things you might think about doing. But the thing that, to me, that's most interesting is if you have some object, right? Some object built, right, built from R, right? So I'm thinking like it could be n by n matrices over R, right? It could be polynomials built over R, right? It could be polynomials in 2 variables built over R, etc. I mean, the point is, it's some sort of standard construction where you're building the construction using coefficients from a given ring, right? If you have that kind of thing, and you have another homomorphic ring, let's say, suppose you have phi, which is a, well, I'm sorry, we're using theta, aren't we? If you have theta is a ring homomorphism from R to S, then there is a natural induced homomorphism from object R to object S.
And this includes, for instance, the field quotients.
Sure. I think that also, yeah, I had to think more about that one. But I'm just saying that there's a chance that this makes sense. I'm not trying to say this is a universal theorem. I have not built the language for that. But and the way you do it is to replace what you do is you replace the object R things. Basically, you take R here and you replace it with theta of R over in the objects. So example 7 is one of these. So it's kind of like this, actually. So he has theta going from R to S, and to keep things, well, you know what, I'm going to keep things less simple. I'm going to build theta bar going from M2 R to M, but you could easily see how to generalize this to n by n matrices. I'll just keep it at 2 to keep my, well, as much as I love the EIJs, it gives you guys less joy, so I will behave. 2 by 2 example. And so theta bar of A, B, C, D is equal to, guess what? Theta of A, theta of B, theta of C, theta of D. And it's relatively easy to show that that is in fact a ring homomorphism from 2 by 2 matrices over R to 2 by 2 matrices over S. In the same token, if I wanted to build, you know, if I've got theta going from R to S again, and if I want to build a new homomorphism theta from, say, polynomials over R to polynomials over S, like this, what I would do is I would say theta bar of A naught plus A1x plus A2x squared plus dot 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 ANX to the n. So there you go, your token polynomial over the ring R. How do you get the corresponding polynomial over the ring S? You just map the coefficients. And you can prove that this is a homomorphism of rings. at times knowing about this, it's very useful. All right. Now, if we take theorem 1, it's very, very nice, because if we put it together, what theorem 1 says, let me summarize theorem 1. Let me summarize it. It basically says rational expressions in R map to same expression in S, replacing I don't even know what I was spelling right there. Replacing, let's say R, or let's say X, with theta of X. And so this writing theta of X, you already see it's really getting annoying. So there is a better way, or maybe I should say theta, or maybe I should say, I said what I said. So we'll write, what I'm slightly worried about here is X is playing a different role in my past example. I hope that's not clouding your mind. So use X bar for the image of the homomorphism, then things are easier to kind of see, right? So in that language, how do we reinterpret theorem 1? Like 1 becomes 0 bar, 0 bar is 0, right? This becomes the image of minus R is minus that, right? This becomes, you just basically, it gives you license to pull things appropriately out of the bars, right? Here. And of course, you might recognize these rules. Can you recognize? I mean, I recognize these rules from like the first week of class. These are the things we said we could do for, I don't need parentheses there. Look what's happening. As I recall, this is what we said for modular arithmetic from the start, right? That really is a prototype for everything that we're doing, a lot of it. So that's what these look like in the bar notation, right? So, and so if you think about that, that's really quite nice, because it says that if I have an equation, right, if I have an equation in R and I map with theta, I have to get what? The same equation in S, right? So there's a connection between solution sets of equations in homomorphic rings. That is actually a very powerful observation. Let me show you how. So this is his example 8, and I can't improve on it, so I'm going to give it to you. I like his example 8, it's good. So he looks at x cubed minus 5x squared minus x minus 17 equals to 0, right? And our goal here is to show it has no solution in Z. Show no solution in Z. All right, so what he endorses is we look at the homomorphism theta, which goes from Z to Z5, right? In fact, this is example, nothing more than example 1 in action with A equal to 5Z. Right? That's what this map is. Well, I haven't written it down yet, have I? But the map is theta of x maps to the congruence class mod 5 of x, all right? So, it's very, very nice. We get x bar cubed minus 5x bar squared minus x bar minus 17 bar equals to 0 bar. Let me restate this more carefully. If there is a solution, right, if there's an integer solution, if there is an x satisfying the given equation, then that implies that there is also a congruence class, mod 5, which satisfies that equation.
Because you take theta of both sides.
Right. Exactly. Take theta of this equation, we get that. Applying theorem 1. And of course, this is very nice because this we can rewrite as x bar cubed, that's 0, right? And what do we got here? X bar cubed minus, come on, I'll get it eventually here. It's x bar cubed minus x bar minus 2 bar equals to 0, right?
Is the choice for C5 just to eliminate that 5x squared term?
Yep. That strategy is not universally successful, as the next example shows. In fact, you know, the details of what are the possible sort of forks in the road here, there are many. But this is often a useful technique to show there are no solutions. I have bad news. Well, one thing at a time. So this, how do you solve this equation in Z5? You got 5 cases. You just plug them in and see if it works. Exactly. So you can test. You know, x bar equals to 0, 1, 2, 3, and 4. And if you do, you'll get, I'll tell you what you get. You get the first one to get minus 2 bar. You know what, it doesn't matter what you get. The point is that none of them work. I'll let you guys work it out for yourself. None work. Let me just illustrate one. If I try, for example, 2 bar, I get 8 bar minus 2 bar minus 2 bar, which is equal to 4 bar, right? Which, of course, is not equal to 0 bar. The others similarly fail. Let's look at example 9. This thing I just erased plays a pretty big role when we study Galois theory next semester, if you stick with me. This idea of homomorphism, replacing the coefficients of polynomials with the homomorphic image, it actually comes up a fair amount. All right, so example 9. Here we're looking at m cubed minus 6n cubed equals to 3. I want to show no z solutions. So in other words, this is what's known as the Diophantine equation, and you're trying to show that there are no solutions, no integer solutions to an equation. So 6 is tempting, but it doesn't help, because in fact there are solutions mod 6. See, the thing is, what happens if you get a solution? Does that mean that there has to be a solution in the integers? It doesn't, because what you're doing when you're studying the congruence classes is you're looking at all possible things in the congruence class, right? And they're all getting lumped together. So if any one of those match up, you get a solution to the equation at the level of the equivalence class. But that does not mean that you have pointwise equality working back. On the other hand, if there's no possible way of matching up points in the equivalence class, you can extrapolate backwards that there's no pointwise matching things. So it's not a reversible thing. I mean, this is good for showing there are no solutions. It's not that. In fact, it's just not useful for showing that there exist solutions.
You could always map to the 0 ring. There's always a solution there. But
That is true, but we could be more severe. If you check your equation and you reduce it mod every possible prime, you can get solutions mod every possible prime, and there still might be no solution in the integers. There are annoying examples out there. Yeah. I'm not going to try to explain, but yes. But yeah, I think that's right. Okay, so here, instead of reducing mod 6, we reduce mod 7. And the answer here is kind of interesting, mod 7. So we'll use Z7. So M maps to M bar in Z7. And with respect to that, what is this? This is M cubed, M bar cubed. What's minus 6?
1.
Yeah, minus 6 is 1. So that's plus n bar cubed equals to 3. And the thing is, if you look at Z7, it has what? It's got 0, 1, 2, 3, 4, 5, 6, right? And if you look at the cubes, cube, what do you get? You get 0, 1, 8 is 1, 3 cubed is 27, which is 6, right? 4 cubed is 64, which is 1. 5 cubed is 125, which is 6. And 6 cubed is also 6. So can you solve this equation, mod 7? No. Because everybody knows that the sum of 2 cubes, mod 7, doesn't work out to 3, right? So this example is very easy to follow, but it's much harder to invent for yourself. Am I right? You know I'm right. What's that? There's doubtless other ways to solve this. You do it with Z3? I don't know. I follow the textbook. I haven't thought about other ways to do it, but I will. I would be inclined to believe you. The Frobenius automorphism is very interesting, but I'm going to leave that to your reading. I must go on here. Something I want to get to today. Let's see here. So I gave you an example from the isomorphism theorem last time, right? But again, the isomorphism theorem, if we have theta going from R to S, ring homomorphism, and then we can define theta bar going from R mod the kernel of the homomorphism, right, to the image under the homomorphism by theta bar of the kernel coset mapping to the image of the representative of that coset. In other words, theta bar of x plus kernel phi is just equal to theta of x. This gives a ring isomorphism, right? And the theorem right before it told us that the image and the kernel of a ring homomorphism are also ideals. Right. So an example which I haven't shown you yet would be the following. If we have A, an ideal of R, and we have B, an ideal of R, all right, then we can build theta going from R cross R to R mod A cross R mod B by how? How about this? Theta of xy equals 2. Right, right, x plus a, comma, y plus b. You can prove that this preserves addition and multiplication, and it maps 1 to 1, right? What is 1? You know, I'll do the 1. Theta of 1, 1 is equal to 1 plus a, comma, 1 plus b. That is the 1 in this Cartesian product, this product ring. All right? For example. Now, great. Is it surjective? What's the image? It's kind of obviously surjective, right? You pick anything in the codomain, it's clear that there's something that maps to it, right? Here's a typical thing. Here's the thing that maps to it. Surjectivity is like immediate, right? So it's on to. So what would the first isomorphism theorem tell us for this map? We get what? We get R cross R mod the kernel of theta is isomorphic to what? It's isomorphic to R over A cross R over B, right? But what is the kernel of theta here?
X and A, Y, B, so A cross B.
Right. Kernel of theta is in fact A cross B. So we get that R cross R mod A cross B is isomorphic to R cross A cross, R over A cross R over B. Isomorphic, right? Not equal. Those are different kinds of objects, right? All right. Moving along here. Oh, yep.
I have a question for example 8. Why do you know we have to map this to 5?
It's a choice.
Okay, I map this to R, okay.
You could try.
Is the result the same?
Well, if you get that it works, that doesn't tell you anything. So you have to, the game is to find a reduction where there's no solution. Knowing that there's no solution in the image, the homomorphic image of the equation tells you that there's no equation in the domain. Finding that there's a solution in the image doesn't tell you anything. So it might be that 4 works, I don't know. Okay, so Theorem 5. Theorem 5 says that if R is any ring, right, we can write K bar equals to K times 1R. What's that mean? Let me just rewrite this. This is, in other words, suppose K is positive. This would be 1R plus 1R plus da 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 plus 1R K-fold times, right? Or it could be what else? I'm assuming K greater than 0 for this comment. But here K could be an integer, right? If it was negative, then we would mean repeated subtraction or repeated addition of the additive inverse of 1. And so he defines Z times 1 in the ring to be the set of all K bars. All right? And what this theorem says is that Z 1R is a subset of the center of the ring, all right? And also what? It's a subring. Yeah, subring. He says the central subring of R, moreover, One, if the characteristic of R is equal to n, or two, if the characteristic of R, what was the characteristic? You guys remember? Yeah, the order of the identity, additive order of the identity. So if that's characteristic n greater than 0, then Z1R is isomorphic to Zn, and if it's characteristic, then Z1R is isomorphic to Z. And the proof is essentially just by the first isomorphism theorem again. So what's the map? He says proof study theta, which is going to be a mapping from what? A mapping from the integers to the ring. By what? Theta of k equals to what? It's equal to k bar. Right? Which again, in detail, means what? K times 1 in the ring, right? We can check that that's a ring homomorphism. Right? For example, if I have theta of k1 plus k2, that's equal to k1 plus k2 times 1r, which by distributivity is k1 1r plus k2 1r, which is theta of k1 plus theta of k2, right? It's not hard to see that we also have this, right? This is what? K1, K2, 1R. Invent a new one. This is K1, 1R, K2, 1R, which is theta of K1, theta of K2. So there you go. There's multiplicative. It's got additive. It's got multiplicative. Is 1 mapped to 1? Yep. So theta is a ring homomorphism. And the fact that it's central is, can you guys see that the image is central? Oh, I'm sorry. What is the image of theta is what? It's k bar, right? Such that k is in the integers. In other words, the image of theta is what we're calling Z1R, right? By the way, side comment. Then the first isomorphism theorem finishes the thought, right? Because if we look at it, we have, you guys are full of, I write an equation on the board, all of a sudden you guys are full of questions. Interesting. It's funny. Where was I? Oh, yes. So Z mod the kernel of theta is isomorphic to what? It's isomorphic to Z1R, right? Because that's the image of theta. But kernel of theta is either equal to nz or it's 0. Depending on whether you're characteristic n or characteristic 0, right? So that's the theorem. Ah, man, I had such high hopes to get to the last end of this section today. My hopes will not be fulfilled. Oh well. I have an interesting example of the theorems in the end of the section, so I'll get to that at least. Now, the definition. If F is a field, then F prime, a subset of F, well, let's say, I don't know, G. G, a subset of F, is a subfield of F if what? Right. Yeah, if G is a subring of the field, right? And so if G is a goodness gracious, a subring, and a subring which is also a field, yeah. So what does that really amount to? How can we test if G is a subfield? Oh, fair enough. Yeah, subring test. I think what I meant to say is, suppose you have a subring. How can you tell if it's a subfield? Right. You just need that every non-zero thing has an inverse, right?
Because commutativity follows.
Right. Very good. Yeah, we have commutativity because it's a subset of a commutative ring. Very good. Yeah. So examples of subfields. We can view the reals as a subfield of the complexes, right? You can view, in fact, here's usual story. Rationals, subset of the reals, right? Subset of the complexes. So the complexes are over the reals are over the rationals, with the usual identifications anyway. Those are, Q is a subfield of both. Shut up. I don't know how to turn this stupid beep off without turning everything off on this silly thing. Anyway, I'm sorry. I will stop being distracted by my phone. Getting to the point here, there's a correlate. So if we have, all right, let's put the pieces together here. Put the pieces together. So suppose you've got a ring, right? For us, that means that you've got an identity. Okay? And so step number one, given ring, right? We can identify a copy of either Z or Zn in the center of the ring. All right, that's what that theorem says. Up to isomorphism, there's a copy of the integers or the modular integers in the center of any ring. Not stupid ring. And so what can you do with that? I can't hear you. Yes, this is what I'm trying to explain. But you're stealing my thunder. Let's see here. So he starts the discussion by saying, suppose R is a field, right? Right? That means that every non-zero thing has a multiplicative inverse, right? And that theorem that we just covered means that there's a copy of something that looks either like the integers or the modular integers in there. So if it's a field, then you can build Q, right? As follows. You can build Q as U the inverse such that what? Such that U and V are elements of what? The integer, the quote-unquote integers, which were, whoa, I feel the board move. No, it's going to hurt. I refuse. Like, it hurts my hands. It's just not worth it. There is some very bad algebra happening on the other side of this board, I assure you. This is not too bad algebra. I mean, it's debatable. Let's see here, V not equal to 0. It depends on a question of taste on this side. It's a question of right and wrong on the other side of the board. But anyway, so what I'm saying is you can build essentially a field of fractions, right, using the integers in the field. Now this is actually a subset. This is an honest-to-goodness subset of R because we're assuming R is a field, right? But we talked earlier, you can build the field of fractions and it may be outside the ring. For example, if we take the integers, we build the field of fractions, we get rational numbers, right, which is outside the ring. But if we start with a ring, that's inside it. So this brings us to the point, which is if you combine this idea with that idea, we get that every field contains within it basically a copy of either ZP or Q, the prime subfield of given field R. It's got to be one or the other, right? Works for division ring too. That may be true, but the corollary here says every field R contains a central subfield isomorphic to either Z mod P or Q according to whether or not the characteristic is P or the characteristic is 0. It means there's a subset of the ring which commutes with the whole ring. But the ring doesn't, it says you're right, every field, central subfield. It does seem rather silly to emphasize central in the context of commutative, but he's doing it, so I don't know why. I mean, I'm right there with you. Why use that word if we're in a commutative context? All right, well, I guess I have to stop. But good news, if you have a general ring, you can make it have an identity. That's the next thing he does. He shows any general ring can be made into a ring with unity by a standard construction now.